Hi everyone, welcome to the video lecture series on understanding natural language understanding. I'm Eric Cambria. I'm a professor of AI at NTU CCDS and a visiting professor at MIT Media Lab. If you have any questions about this course, the contents of these lectures, you can email me at one of these email addresses. And if you want to keep yourself updated with what we do, you can follow us on any of these channels. So who is us? We are the Centric team. We are a team of about 20 people at NTU CCDS, some postdocs, PhD students, interns, master students. If you want to know more about who we are and what we do, you can check out this link. And you're welcome to collaborate with us and even join us. So this mini course is about data science and AI. And if you're an expert of AI and machine learning already, maybe you can skip the first two lectures, but maybe it's still good to look at these basic concepts from different points of view. So the contents of these lectures are actually in this textbook, Understanding Natural Language Understanding. And in the book, you can find also a lot of extra materials, videos to watch, exercises, reading lists, code from our GitHub, an assignment, and a quiz. So let's get started. The first lecture is about data science. These are basic concepts about how to represent data and how to classify data. So I'm sure you've seen this picture before. It's about the importance of data and AI in this new era of artificial intelligence. So data in the context of AI, these new AI tools, is very important because it affects how your AI models will work. And this is a bit of a shift from what happened in the past. For example, when I was a PhD student, people were very much willing to share their data, but they were very protective of their codes. And now it's a bit of the opposite. Even Google is willing to share with you their code because they know that without their massive amount of data, you have no chance at replicating their results. And so actually, there's a lot to talk about how to even store data. In this paper from 2017, we discussed how long is it going to take before we actually run out of space to store data. And so people have started looking at DNA-like structures to store data, or Microsoft, for example, is looking at holograms to store data. But as you know, it's not just about the volume of the data, it's also the variety, the fact that data comes in so many different formats, the velocity, the speed at which you need to be able to process some of the data, and finally, the veracity. How much can I trust my data sources? But what is data? When we talk about data in terms of numbers, numerical data, then it's easy to understand. But when we talk about text, it's slightly different. We kind of have to translate or convert text into a numerical format and then do some computations and then revert it back to the text format. So this may seem something normal to do, like we do, for example, for the Fourier transform. But we could talk about whether this is the most efficient and cognitive-inspired way of doing this. Like, is this really how meaning is encoded and decoded in the brain? So, since we have no better way to represent data at this point, text data, we're going to be looking at these three main ways to represent data. So one-hot encoding, bag-of-words model, and word embeddings. Today, of course, word embeddings are what are used most, but to truly understand word embeddings, you probably need to have a look at one-hot encoding and bag-of-words. What is one-hot encoding? Well, simply you have a vocabulary of words, like you can see here in this example, and then to convert a sentence like this, S1, into a numerical format, you just use ones and zeros to encode presence, basically. If this word is present at least once in the sentence, you put one, otherwise zero. So this, you end up with a Boolean vectors that tells you that translates the sentence into a numerical format. A bag of words model is slightly more advanced because it also takes into account the frequency, but it still doesn't take into account context. That's why it's called bag of words, because it's the same as throwing all the words that make up a document into a bag and scramble them. So word embeddings are more advanced because they can finally encode context. That's why it's also called CBOW, continuous bag of words. We'll talk about word embeddings later, but this is the state of the art in data representation today. But let's take a step back to understand how this works. In the Boolean model, in the one-hot encoding, we again use ones and zero to encode presence of a word into a document. So here what you see on the columns are documents. These are the plays of Shakespeare. And based on these numbers, based on the presence or absence of specific terms, I get these vectors, which in this case, because I'm only using 7 words, are 7-dimensional vectors. So this is efficient because you can do Boolean operation between these documents to see, for example, how similar they are to each other. Then if you start counting how many times each of these words appears in each of these documents, then you have better information and you get a count vector, which is what it's used in a bag of words model. Then there are different ways of improving this. If you use TF-IDF, you end up with some weights that can tell you even more how relevant each word is to each document. But the important concept here is that we are really converting these plays, these documents, into vectors. And why is this useful? We'll see that later, because then I can classify these documents, or I can compare them to see which one is most similar to another, which normally you couldn't do so fast. You would have to read the whole play and then, based on your own understanding, then do this kind of tasks. So here we have, again, 7-dimensional vector spaces. What does this mean? So it's easier to start from the beginning. When I have to represent a point on a line on a monodimension, I just need one coordinate, right? Then when I go into 2-dimension, I need 2 and finally 3. This is something that we are confident with. We perceive the world in 3 dimensions, right? So this is my point in space, which is also my document in case I only have 3 dimensions. And I can represent this as a point in space or as an arrow that goes from the origin of the space to the point. And here's another example of this. So if I have just 3 words, 3 dimensions in my pool of documents, color, vehicle, and motion, then I can use this to represent other documents that are about car, aircraft, and so on. And based on how these are represented in this new 3-dimensional vector space, then I can calculate, for example, how similar they are to each other. But this is an important question. So this is how I represent data, good, but then what do I do with it? How do I actually calculate the similarity between these documents in this new vector space? Let's take another step back and look at this bidimensional vector space. I only have 2 words, 2 dimensions here, gossip and jealous. So let's say that I have a query Q. You can think of this as another document if you want, but let's say I need to find the most relevant document between D1, D2, and D3 to Q. So clearly, D2 is the most similar one because it contains an equal number of gossip and jealous. This query is probably a query like jealous gossip. So this is important to look at because if you calculate the standard distance, like a Euclidean distance between this point and this point, it's actually very far. You probably get that D1 or D tree is more similar. Why? Because it has a smaller distance from Q. So this is why instead of calculating the Euclidean distance, we look at the angle between these vectors. This is also called cosine similarity. And you can understand this if you just take the same vector, the same document D, and you copy paste it into itself and get D prime. When you do that, the length of the vector will become double, but the direction will be the same. So this is ultimately the same document, and that's why we look at the angle and not the distance, because if I calculate the distance between this point and this point, it will be some number, but if I look at the angle between these two, it will be zero, which is exactly what I want. There is no difference semantically between these two vectors. So that's exactly why in natural language processing and information retrieval, we use cosine similarity. And to calculate the cosine similarity between two documents or between a query Q and D, this is the equation, which sounds a bit complicated, but actually it's not if you normalize the vectors. If you normalize your vector space, then it becomes a dot product or scalar product where you basically just multiply the two, the different dimensions one by one, and then sum them up all together. So far we have been looking at toy problems with 2, 3, maximum 7 dimensions. But in reality, you can imagine that as you add more and more documents, then you have these huge vector spaces. How can we actually compress them to be able to work with maybe a few hundred dimensions only? There are several ways of doing this. It's called dimensionality reduction. One simple yet efficient way to do this is through SVD, singular value decomposition, specifically truncated SVD. So one beautiful property of matrices is that you can factorize the matrix this way. So this is the same thing that you do when you, for example, factorize a number like 6 into 3 multiplied by 2. The same you can do with matrices, and you have this U sigma V transpose matrix that equals X. So if I remultiply these three, I obtain X. But what's cool about this is that this sigma matrix in the middle is actually a diagonal matrix. So there's nothing in the top right and bottom left corner. These are all zeros. The only known zero values are these values in the diagonal, which are also called singular values or eigenvalues. And what's also even more cool is that they are ordered from the most important to the least important. So if I start removing some of these singular values from the bottom right corner, and then I remultiply the matrix, basically what I'm doing is that I'm reducing the dimensionality of the matrix. So that means, for example, that if I'm in a 3D vector space like the one we saw before, I remove one singular value and I'm back into 2D. What does this mean? It means that I have a smaller space where the distances are preserved. The distances between points, data points or documents in this new space are preserved. It's a little bit like taking a picture of a 3D object. You go from a 3D space into a 2D space, but of course the distances between every point in the picture are preserved. So this is a cool way to be able to work with a huge number of data points and dimensions in a smaller space. So this is nothing new. This is also how JPEG, for example, works. This is the original picture, which is actually from Playboy, that the people that invented JPEG came up with, they used. But this is a good example to see what it means to do dimensionality reduction. Here in the original picture, you have 512 eigenvalues. If you cut off half of them, so again, you take off the half from taking from the bottom right corner of the sigma matrix, you get a picture that is much smaller in size in terms of the memory occupied in your computer, but as you can see, there is not much difference in the quality of the picture. And if you continue doing that, you can see that the value, the quality of the picture is still more or less the same. Then, of course, if I keep cutting away too many singular values, I get a very blurred picture. So this is also an important point in terms of you need to find the best trade-off in the dimensionality of your vector space and the quality of the data representation, because then if you compress it too much, every point is going to be so close to each other that you won't be able to do anything there. You won't be able to calculate any distance. But so this is how it looks when you go into more than 3 dimensions. Maybe for us, mere humans, is not easy to understand, but for a computer is not a problem to work in hundreds of dimensions. And so here is a snapshot of affective space that does exactly that, to visualize and represent concepts, natural language concepts, words, and multi-word expressions in this multidimensional vector space. So what do I do with this once I have this representation? Well, I can calculate the distances between different points to know how similar these are, or I can use this for classification. So for example, let's say that I have 3 classes of documents. I can use the distances between a new data point between the centroids, the center of gravity of these 3 data clusters, to then classify this new document as belonging, in this case, to the class environment. What is a centroid? Is the center of gravity of a cluster. You can think of it as the most central point to the cluster, and we can use that to calculate a distance between the new document and each centroid, so that the smallest distance will tell me which class this new document belongs to. And again, when I talk about distance, we can talk about different kinds of metrics. The most standard one will be the Euclidean distance, as we mentioned, or the cosine similarity. But there are other kinds of more topology-aware metrics that you can use. So when we talk about classification, actually, there's many ways of performing classification. And here you have a few examples. You use regression when you have to kind of predict what is the trend of your data. For example, for financial forecasting, discriminant analysis is similar to what we just discussed when we talk about SVD. Prototype methods is like k nearest neighbor that we'll talk about later. Support vector is also something we'll talk about later. ROC and probability. So I want to discuss a bit about probability before we end this lecture, because it's a basic concept, but still very important to then understand more advanced machine learning models. So the easiest thing that you can think of when you talk about probability is a naive Bayes classifier. So let's say that we have we represent a document, of course, as the combination of the words X that make up this document. So if we have to classify this document, basically we are looking at which class C this document belongs to, given the words that make up the document. So this would be a probability that is very difficult to calculate, right? But we can use the Bayes rule to convert this probability into this new probability. And this is easier to calculate, right? First of all, we're looking for a max. Why a max? Because, for example, I'm calculating the probability of this document to belong to class C1 versus class C2, and I will have to take the maximum probability, right? And so since I'm looking for a max, the denominator doesn't really count. PC is the probability of the class. That's very easy to calculate. The only thing that I'm left with is this big probability, which again would be difficult to calculate unless I assume that each word is independent from each other. So if I do that, then this probability becomes the product of all the small probabilities that I can easily calculate from my training data, right? I can look at how many times this word belongs to the class C in all my training documents and easily classify this. So this is the simplest yet effective way to calculate, to perform classification. What's the problem is that it's called naive because it naively assumes that each word is independent from each other, but the reality is different from that, right? A lot of words, because they belong to the same domain, and how I do sentence structure, they will be actually very much related to each other. And then another problem with doing this big product of probabilities is that even if one is zero, then the whole thing will go to zero. That's why we do +1 for each of these small probabilities and plus k to be able to counter this problem. So this is just one of the fixes that I can do to calculate naive Bayes classification. Another similar approach is the k nearest neighbor, which is similar to what we saw before. So if I have a new document and I want to classify it, before we calculated the distance between this and the three centroids of these three clusters. Another approach is to just look at the neighbors. How many? K neighbors. That's why it's called k nearest neighbor. If I decide that k is equal to 6, then I'll just look at the 6 nearest neighbors. So instead of calculating the distance between the centroids, I'm calculating the distance between the 6 nearest neighbors. And then based on this, I will classify. So in this case, as you can see, 5 out of 6 neighbors belong to the class environment, and that's why I will classify this new document as environment. So here in this picture, we can see 3 different kinds of separators. The yellow one would be a line that I manually draw to separate perfectly the two classes, the empty circles and the full ones. And then you have the white lane and the red one. Can you guess which is which? Look, so one is naive Bayes and one is KNN. Naive Bayes looks at the probabilities, so it's a linear separator. That's the red line that tries to cut the space into 2 halves as best as possible based on the information that I have from the training data. While KNN is more, as you can see, it's the white line, because I'm looking at the neighbors each time is a bit more fine-grained. So it's more, it's able to maybe separate the data a bit better. So which one is better? It depends on the data. Both have their own cons and pros. So KNN tends to be high variance and low bias. Naive Bayes tends to be the opposite. What does it mean? For example, if you're trying to classify trees, high variance and low bias means that you are basically overlearning. You're learning so much the features of your training data that then if you change even a small thing in the new object, then you will not recognize it as one of the belonging to the class, which is bad. You're too much, you're learning too much, you're overfitting. And the opposite is bad too. If you have low variance and high bias, then you are a lazy botanist who said yes to anything that is green is a tree. So this is an important concept in classification. If you have high bias, you're underfitting. If you have high variance, you're overfitting. You want to find a trade-off, a good compromise between these two. And this is exactly why neural networks became popular, because instead of having to choose between one of these two, they were finding a good trade-off between bias and variance. Support vector, as we mentioned earlier, is another good way of linearly separating a space into two classes. And this is something that today is considered a bit outdated, but it's been the state of the art for more than 10 years in computer science, and can still be used if you have a data space that is linearly separable. So what does it mean to separate linearly the space into two halves? It's just drawing a line to separate them. But then the question here is, which one is the best line, right? Because potentially I have infinite possibilities. So the power of support vector machine is that it's calculating the gap between the data points at the border, which are the support vectors, and making sure that this is the maximum gap between these two. Because, for example, if I take this other line, the gap between the support vector will be very small. And this is how SVM works. It calculates the margin row and tries to maximize it. So I won't bother you with the details of SVM. You can look those up if you're interested. But again, it's a very smart way of linearly separating two classes in any vector space. And you can still use that if the data is linear enough to allow this. And there are a lot of tutorials and packages for SVM that you can use. So the last thing I want to cover for the first lecture is clustering. So what do you do when you don't have labels? So far, we've been talking about classification where we had a specific set of classes. But what if I don't have classes that are known a priori? Well, I can still use the centroids to look at the structure of the data. One famous algorithm in this context is k-means. And the way it works is that I pick two seeds randomly in the data, and then I assign the rest of the data points to the nearest seed. You can think of this as the centroid at first, although it's not. And then you actually compute the centroid. How do I compute? Again, I'm looking at the sum of all the distances of each point to the center of the cluster. So in this case, when I compute the centroid of the red cluster, I will get this point, and this obviously will be the centroid of the blue cluster, which is almost in the middle of this tree, right? So what do I do next? I reassign the data points based on the new centroid. So obviously these points here will become blue, right? Why? Because they are nearer to this x rather than this x. So I then recompute the centroid, which will change position now that I have new data points. And I do this until nothing happens, until the algorithm converges. And so this is a very simple yet efficient way of finding and separating clusters in a vector space. What's the catch here? Again, I need to decide what's k a priori, which can be tricky sometimes. In a case like this, it's evident that I only have two clusters, but in other cases, it may not be. Also, we were having that example in 2-dimension, but when you start working in many dimensions, then things get slightly more complicated. But still, it's a good way to classify data when you don't have labels. And there are different ways of calculating how good your cluster is, and also different strategies that you can apply. So if you don't like the fact that, for example, a centroid actually ends up in an empty space, an empty point of your space, you can actually go for a k-medoid approach, where you just take the nearest data point to the centroid so that you have a better idea of what that class can be. Because once you do clustering, then you may want to label those clusters as something meaningful. So this wraps up lecture 1. And this is a final slide that summarizes the difference between classification and clustering. And so in this lecture, we'll learn how to represent data, how to classify it, and how to do clustering. I hope this is clear. If you have any questions, feel free to email me, and see you at the next lecture. Ciao.